Hello and welcome to TidyX episode 59. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Warden. You can find me on Twitter at OSPPatrick. You can find our screencast on Twitter at tidy_explained. You can hit us up on Gmail, tidy.explained@gmail.com. You can like and subscribe to the YouTube channel and comment there. Some people have been putting in great comments. We had some cool coding solutions from Mike Parrott 2 weeks ago, which was really useful. Or you can open an issue on the GitHub page and let us know if there's something you'd like to see.
Yep, exactly. Yeah. All right, so episode 59. So we're going to continue, once again, the pitch classification series we've been doing using machine learning models to predict pitch class. But this time we're going to do something a little bit different. We keep on talking about how our models are being impacted by this massive class imbalance that we have. And so we wanted to take some time to actually investigate that and see what's going on and share with y'all, different strategies that you might use when you're dealing with a very imbalanced data set. So I'm going to share the screen so Patrick can now see it, and then we'll get this thing going.
Probably can yank about 2 more screencasts out of this series, and then we're moving on.
Moving on. Let us know what you want us to cover next. Put a comment in the YouTube video down below so we know what content you are searching for, because we want to make sure you are getting what you want out of this. Because we're having a lot of fun doing this just in general.
Yeah.
All right. So, quick reminder of what's going on here. So, we were, quote, hired by the Fantasy Baseball League to try to come up with a machine learning model that can make predictions of the pitch type, because currently they have a person sitting in the stands making calls of what the pitch type was, and that's clearly a huge waste of a person's time when they could maybe be doing something else. So we got a bunch of data using the MLB Game Day package, pulled a bunch in, did some cleanup. We did that in episode 53, I believe.
So we're probably six or so in on this.
Yeah, so 53 or 52, where we went through and did a bunch of cleaning. So we're not going to spend any time on that. So we're just going to load in that data there for us to use. And we're now going to start talking about imbalancing. So what is imbalance?
So imbalance is basically, if you've ever picked up a book on machine learning, they always give you these fun examples to work on to teach you something. And they're always like, hey, here's the iris data set, and every class has the exact same number of observations. So every class is balanced. Or the famous one from the ML bench package is the Pima Indians diabetes data set. And it's like a 50-50 data set. It's like, unfortunately, in real life, I've never, I don't want to say never, but I've rarely had it happen where everything is totally balanced. So usually what we're dealing with in real life is we see a whole bunch of observations for one class and a lot less observations for another class. And one of the issues that you can run into with that is that a lot of models or machine learning models depend on or like when the classes are more balanced, when there is a closer to evenness in the number of observations. And so for this data set, we've been dealing a bunch with class imbalance where the four-seam fastball has been the dominant class. And to visualize that, we're just going to use this quick little GG plot, GG label plot. So we take our cleaned data, we're going to count the pitch type to get the number of pitches observed within the data set. And then I want to turn that into a percentage. So within the plot, I can present that as another piece of context. So all I do is I calculate a new variable using mutate, and that new variable is called percent. And I'm going to divide that column n, each observation in column n, by the total of column n. That's going to give me a percentage column. And then I'm going to pass that into ggplot. So on the x-axis, I'm going to have n, and on the y-axis, I'm going to reorder the pitch type by n. So basically, it's going to be a horizontal bar plot from largest to smallest observed pitch. I'm just going to do a little, make it pretty there by doing a geom call and make it light blue. And then I'm going to put in the labels of the percent. So I'm going to say geom label. And what I want to do is I want to label the percentages, and I want to make sure that they're labeled as percentages, because obviously if you look at mutate there, I'm going to have a decimal number from 0 to 1. So I use the scales package, which I call. I give 2 little dots since we explicitly didn't load that package to start out. So I go scales, : and I use that percent function. And then I put in the argument of that percent function, the percent column that I calculated. That's going to make a nice little percentage.
All right, and here we go. And here is our class imbalance. So as you can see, you don't have to look very hard. The four-seam fastball, 37% of all the pitches we are seeing are going to be four-seam fastball, which means if our model wanted to be pretty slick, all I'd have to do is call four-seam fastball, and it would automatically get 36.94% accuracy.
Yeah, and you can see the ones that we've constantly had problems with when we've looked at our within pitch type accuracy has been those 2 at the bottom, the KC, the knuckle curve, and the FS, which are substantially smaller number of observations. We're going to look at those in a second when we try and handle this, meaning we're going to look at the number of observations here in a second.
Yeah. All right. So let's first get a baseline model going for us to be comparing all of the rest of our models to, because it's always about comparing different models, right? You want to see how one model does compared to another, and then look at it in the bigger context of, okay, what am I actually trying to do? So in episode 55, we trained a bunch of random forests to as one of the machine learning models, and we're going to use that as the reference model because it's able to train relatively quickly for us. So what we're going to do, if you want to learn more about it, watch episode 55. We have the linky here, bit.ly/TidyX episode 55. So first we set our seed so that if anyone else comes up to run this, they should end up with the same values unless they're running an older R version. Then we're going to use the RandomForest function from the I forget which package. Is it the RandomForest package?
Yeah,
of course. A RandomForest package. We're going to use the formula expression here. So we're going to do pitch type tilde dot. So what this is saying is I want to call pitch type against tilde dot. And the dot represents all the other columns that exist in that data set there. The data we're going to be passing is train cleaned, which is the unchanged data set, and we're going to use an mtry of 6. So this is just, that's using some basic model parameters that we determined were pretty good to start out with.
Yeah, this is the exact same model from episode 55 with the exact set seed. So we should, in theory, have the exact same output. And if you're just jumping in on this episode and you want to see more about that model and optimizing that model and all that stuff, episode 55.
All right. So now we're going to pull out the predictions from that model. We're going to get the type class so that it just returns a simple vector of the actual called classes, and we're going to add it into this test clean data set, and we're going to reassign it to test rf pred. So we get a quick head of that. So there we go. We've got our rf pred column here with the predictions from our basic model. If we do a quick table of this, hey, there's our confusion matrix of the different ones here. As you can see, the four-seam fastball clearly called the most easily amongst all the different classes here. Okay, let me zoom in actually a little bit. I realize I'm relatively far out, so all right, so we zoomed in here. Now let's get a quick peek at the within pitch. So this is the same sort of method we've been using the last several weeks here. So we count the predicted and actual pitches, then we group by the actual pitches and get, okay, what are the total number of pitches that actually exist? What are the ones that are called correctly, and which are the ones called correctly out of total number of pitches? And so you can see for
out of total number of pitches for that pitch type.
Yes.
By that pitch
Yeah.
type.
Yeah. Excuse me. Yeah. So you can see four-seam fastball hitting like 90% here. So you can see FS and KC are hitting like, under 19 or basically 18% and basically 23%. So not so great. And then the total accuracy of the model itself is we get the number that are called correctly divided by the just total number of pitches, and we're hitting an accuracy of 75%, which, I mean, depending on the situation you're working in, 75% is actually pretty solid. In our case, we want better.
Or we want better, or we want the same, but we want to be able to identify some of those other smaller observed pitches at a more accurate rate.
Mm-hmm.
Yeah. And so to handle this, we're going to try and downsample and upsample our data. We're going to use the Caret package for this. There's another package called Rows that will do upsample and downsampling, but it only works for binary data. So the Caret package is super handy, and it's going to work for this multi-classification problem. And so first thing, let's just take a look at the number, the raw number of observed pitch types in that cleaned data set. So here we can clearly see the lowest are FS and KC. So 436 and 600 observations relative to the four-seam FastBall, which is all the way up over 9,000, nearly 9,500.
It's over 9,000.
Yeah, 9,500 observations.
Reference
right?
for all y'all know.
So for downsampling, what the function from the Caret package does is downsamples the data so that basically it goes through each class, and it takes a randomly generated sample from each class to the number of the lowest class. So in this case, the FS is 436 observations. So basically what downsampling is going to do is it's going to create 436 observations of every pitch type. Now, there's a limitation here, which is that we are throwing away a whole bunch of data. We've essentially thrown away 9,000 four-seam fastball pitches. So throwing away information can sometimes be really problematic. And so you really have to be cautious when you downsample, and you're going to see how that affects the model. Conversely, upsampling does the exact opposite. What it does is it says, hey, take a random sample with replacement of every class until they have the same number of observations as the highest observed class. So remember, the four-seam fastball had 9,405 observations. We've now randomly sampled with replacement every single pitch type to obtain 9,405 observations. Now, the limitation with that is that, let's say, for example, KC was or FS were the two smaller classes, and we just upsampled them with replacement to 9,405 observations. If what we were, the observed data that we're upsampling from is not representative of the population, we've essentially created 9,405 observations of information for a pitch type that really isn't going to tell us anything on our test set when we actually go and try and make predictions in the wild. So there's a limitation there that you have to be aware of. So with both of these, what is it for Spider-Man? With great power comes great responsibility. So you always have to weight these things and be aware of the limitations. Nothing is, there's no free lunch here.
Exactly. So you might be, you really got to hope that four-seam, or the FS, I think that's stood for split finger.
I think you're right.
FS split finger. Ha-ha.
Yeah, split finger. There you go. Finally
we're getting
7
episodes in.
Yeah, whatever. You got it.
That you got to really hope that is truly representative of the population, because any signal that exists in the data you currently have is going to be amplified.
Yeah, that's right.
All right. So now we're going to train our models to see how they do. How does upsampling do? How does downsampling do? And really, we're basically going to be following the same process that we did before to train it. I mean, it ends up being a really simple addition now that we've generated this new data set. The only difference is now the column name. It used to be called pitch type. Now it's called class, because that is the output from upsample and downsample, is creating the column called class, because it didn't know what you called it originally. So we're going to now train that. So now first we're going to do the down sample one, and that runs fairly quickly. as we'd expect, because it is a smaller data set. There's just not as much to chug through. It's just smaller data. So now we've now trained this new model here. We're going to pull out the class once again and bind it to this test rf pred. So now we get the original and then the new downsampled random forest, which you can see
they have some discrepancies.
They already have some differences here, but here they're the same. Here they're the same. So I mean, you never know. Could be finding some new stuff that we didn't see. Let's take a quick look at the confusion matrix there. I don't know. Whenever I look at confusion matrix, especially this large, I'm like,
Yeah.
I mean, it's kind of a lot to try to sort through.
Yeah.
But like here, the four-seam fastball, it's a little bit lower.
I guess we could have saved the confusion matrix into its own data frame and used like core plot and made like a heat map of it.
Yeah.
Something interesting.
Future us.
Next time. Yeah, future. Next
All right,
time.
now we're going to run the same within pitch call here. And, interestingly, or I guess not interesting. I mean, depends, because now we have balanced classes. There's not one that's really dominating. There's
Correct.
not, or not one really dominating and not one that's being like called really, really poorly. I mean, they're kind of mediocre.
Yep.
Like the CH changeup. Yeah, changeup, curveball.
Cutter.
Whatever. Anyway, there.
No. FC I think is cutter. CU is changeup.
I mean, to me, that makes sense at least. But
KC is knuckle curve.
But yeah, I mean, we don't get anything higher than the changeup.
74%. Four-seam fastball looks like 74%.
But like, we lost a lot of prediction in the ones that we see a lot of.
Yeah.
But then we also gained a lot of power in the ones that we don't see a lot of.
For example, KC went from 18.3% to 56.1%. And FS went from 23% to nearly 66%, that is.
I mean,
but we have a number of errors with some of the other classes now. So if we actually calculate the model's overall accuracy, remember we were at like 75 or 76%, we've lost nearly 10% of model accuracy.
So,
what if we try the upsampled data?
All right, let's see what happens with the upsampling. And this is going to take a moment to chug, because before, right, the maximum number of records that we had was 9,400, and that was for the four-seam fastball, and that was substantially higher than all the other classes that we had. Now all of our classes have 9,400 samples.
Yeah. So this is going to grind for a bit.
This is, we have, 9 classes? 9 classes times 9 times 18. No, brain cannot do math anymore. It's been a very long day. 81. I can do maths. It's basic. I think
the maths. Yeah.
Yeah, I think it's like 81,000 records now.
Yeah.
As opposed to like, a couple thousand. Or I
think we had 20-some thousand, 26,000.
A lot bigger now.
Yeah.
It's still having to chug through a lot of the scene or a lot of data now.
So it's going to grind for a while. Notice that we always set the seed before the models. And also when we did the downsampling and upsampling, because those are randomly sampling, we also set the seed there. So for anybody who's never set the seed, basically those numbers are essentially random numbers. Like I literally just kind of close my eyes and I hit a few keys and get some numbers out. And as long as it's consistent for, let's say for Ellis, when I send it to him, he'll get the same output as I get. If he doesn't set his seed, or if he doesn't run that line, or if he changes those numbers, he's going to get something totally different. And it's just because the computer, when you set that seed, is working with a pseudo random number generator. So it's basically saying, oh, okay, if you want some consistency, here's the way to do it, right?
Mm-hmm. Yeah. All right, cool. So that's a good segue, or a good side for random number generators, because I think they're fascinating.
Right.
and how they all work. And then R changed its random number generator because they found some weird imbalance and like some
is that right?
edge case, which is why it changed from 3.5 to 3.6.
Oh, interesting.
There was they found some weird edge case where it wasn't actually random, it was imbalanced and biased. So changed that. Random fact. Why I know that, I don't recall why that stuck in my head.
Yeah.
But now you do too.
There you
All right,
go.
so now we have our fit random forest here. We're going to do, once again, pull out the class, add it in, take a quick look at the output here. Let's see if I can get it all on the same row. There we go.
Oh, there you go.
There we go. All right, so we've got the pitch type, the original pitch type, the called from our original random forest, the predicted from our down sample, and the predicted from our up sample. So interestingly here, down and up both matched for this one. They both think that this pitch number, this first pitch here should be an FT. It is in fact actually an FC.
All three of them got it. Yeah, you're all wrong.
We're great at machine learning, everybody.
It happens.
Here all of them got it right though. We're really good at machine learning.
Next line too.
Cooking with fire now.
Right.
All right, we're getting 66% after 3. All right, so let's take a quick peek at the confusion matrix. Once again, it's kind of a lot. I just kind of gravitate to this FF because that is the largest number. And it's better. Better than the downsample.
It looks like it is.
Than the regular.
It looks like there's less off-diagonal stuff. Let's take a look at the within pitch class type and see. And maybe, so that's the new one. Can we scroll up and pull the old one? Or just remove the...
Oh, this is the old one. Yeah, we
there it is.
Yeah.
Okay, and I think you need it down. No. Yeah, on the other side of those equal signs, right? Yeah. There you go.
Derp.
Okay.
Excuse me. So this
now,
upper one is the original model that we had, and the second one is this upsampled data set model that we have.
So let's take a look. So the bottom is the new one, the upsample data. And let's start with KC, which was our small observation class. Originally, we were at 23. So we're at about 26 and a half, maybe 27-ish%.
So
not bad.
Bumped it up a little bit.
Bumped it up. FS was another small sampled class. We went from 18.3% on the raw data to about 27% on the upsampled data. We lost a little bit if you look one row up on the four-seam fastball. So we classified about 87% accurate there and about 91% accurate on the raw data. But overall, we're looking like this is pretty competitive. For example, FC, if you look above, that's another small sample class. We hit 46.2%, and there we hit 41.1%. So we can see that some of the classes that had more observations maybe lost a little bit, although cutter or changeup rather is still 807. Some of these more represented classes lost a little bit of accuracy, but we seem to be doing better in the upsample data with the smaller classes, and we haven't really lost a ton of overall accuracy when we've done this. So if we run that, we're at about 75%, and I think with the original model, we were also at about 75%. So we're pretty competitive. Let's compare these three models and talk a little bit about that. And I think what we'll do for next week is we'll compare all of the models that we did and maybe use some upsampling and downsampling for all of those models and see if any of them...
What's going on with all of it?
any of them were better or worse or whatever. So we're going to use three measures for comparison. We're going to use log loss, Brier score, and then the ROC AUC. And I'm going to explain these in a very small kind of like high level detail. We're going to use some packages here to help us. Because we have 9 classes, these things, if you do them by hand, can get a little messy. But if you want to see them by hand, on multi-class, we can always open up an issue on the GitHub, and I'll do them by hand.
We asked to do this because it can be painful.
I'd be happy to put together a short tutorial on doing it by hand, which is always good if you can. It does help you understand these things a little bit. So we're going to use some libraries there. I load them and I tell you which model comparison technique we're going to use those packages for. The first one we're going to use is log loss. So if you think about accuracy is basically hit or miss, right? It's a binary. You either classified it correctly or you didn't. But really what these models are doing, or any logistic regression, they're predicting a probability that the probability of an outcome of one of the two classes, or in this case, one of the 9 classes. If we simply go off of a measure like accuracy, a hit or miss type of measure, what happens is, let's say our threshold for classifying one class is anything over 50% is class 1 and anything under 50% is class 0. That means that if we predicted a 51% probability of being class 1 and a 99% probability of being class 1, both of those would be considered a hit, even though they are miles apart in magnitude. And so what log loss does is it represents the closeness of our prediction probability to the actual observed value within the data set that we're building the model on. And so the further away from the predicted probabilities, or from the further away that the predicted probabilities are from the true value, the higher the log loss. So we want a lower log loss as much as possible. So for example, if we predicted 99% that it was class 1 and it was class 1, we get more credit for that than if we predicted 51% that it was class 1 and it was class 1. And so that's what we're going to use in order to compare these models. So what we need is the actual probabilities for each of the classes. And so Ellis is going to go ahead and bind those in.
So what this is doing is outputting a matrix from this predict function here, but we're assigning it to an actual column itself. So it's actually going to be creating a special, because these are tibbles, a special type of object where the column actually represents a matrix.
Yeah.
So
if we remove that, I think it would just bind the.
It would make it white. I don't want to do that because I don't want to mess it up. But.
Yeah, no, and the reason why I did that, you'll see when we run the actual functions, is it makes it a lot easier than selecting a whole bunch of columns. So.
Exactly. So actually, we can run this now too, can't we?
Yeah, so we're going to start with log loss, and we're going to run the multi-log loss, which is sometimes referred to as cross entropy. If you remember the previous screencast where we used neural network, we set our accuracy metric when we were validating the model to be cross entropy, or CE. So same kind of concept here, and we talked a little bit about it there.
Yeah.
So again, lower log loss, the better. So here at the first one that we see is our
original model.
Original model, that's right. The next one we see is our downsampled model, where we threw away some data, and then the bottom one we see is our upsampled data, our upsampled model, which is again pretty darn competitive with the raw data model. So we're doing pretty good there, and we also like that some of the within class predictions were higher. So far it seems like the upsample model we'd be pretty excited about. One thing you can do is calculate if you have a balanced data set. This gets a little different if the data set is unbalanced, but we made the data sets balanced by upsampling and downsampling. You can calculate this simple little dummy log loss, which is basically if the model were to, if you were just to guess what one of the 9 pitch types were. So you get the number of classes, which in this case is 9. I just hard coded it there in case something were to ever change in data. And the dummy log loss is calculated as the negative log of 1 divided by the number of classes. And so in this case, it's about 2.1, 2.2.
So like that's base model if you're to randomly guess.
Exactly. So yeah, an intercept only type model, right? So we're doing pretty good with any of those models, but it seems like the upsampled and the raw model are the better of the better of the 3. The Breyer score is another way to compare models, and this is another comparison type that takes into account the probability predictions. And so if you think about like a continuous classifier, like a linear regression or something like that, where we use a mean squared error, we might use a mean squared error to compare our models. That's exactly what the Breyer score is, just for a probabilistic model. Again, it's comparing the probability or the closeness of the prediction to the actual observed outcome. And so what the Breyer score is, it's the average of the mean squared error of the predictions. So just like you would do in a linear regression. So we can go ahead and we can run our multi-class Breyer. Again, lower is better. So we see the middle one there, the downsampled model is doing a little worse than the raw model, or I'll call it raw model on the normal data set, and then the upsampled model, which are, again, relatively close. 0.35, they're pretty competitive with each other. And the final method of comparison that we're going to use is we're going to use the ROC, and really we're going to use the AUC, but the ROC is basically a plot. It's a way of representing the sensitivity and the specificity, or 1 minus the specificity on the x-axis. And what it is it's showing the optimal cut point for the model, whereby you want to get the largest area under the curve, meaning that you want to be classifying correctly as much as you possibly can. So if you think about the curve, you'd want the curve to be pulled all the way up and to the left as high as possible. And the AUC is basically the value that you're interested in here, which is the area underneath that receiver operating curve, area underneath the receiver operating curve, AUC. An AUC of 1 is like the best model ever, which you'll probably never see unless you're totally overfit, which is you get everything right. Model 0 or AUC 0 is a model that does everything completely wrong. And AUC of 0.5 is a model that basically you should just probably flip a coin, because it's take it or leave it. It might get it right. It might not. It's not any better than random guessing. We want as much or as high an AUC, counter to the Breyer score, the log loss, which we wanted lower values. AUC, we're going to want as high or as close to 1 as possible. So we can run our multi-class ROC and pull the AUC.
He's put a lot of messages out, so he wrapped it inside of a suppressed messages, because we just didn't, in this situation, we didn't want to have a bunch of messages. We just wanted to directly look at the results of the ROC.
Similar to the other functions, literally all we're passing this is our short little matrix of probabilities and our outcome. Actually, for this one, we're not passing it the probabilities. Sorry, the other ones we're passing it that matrix of probabilities. For this one, our predictor variables are the actual predicted class, and then we throw the little $sign AUC at the bottom, at the end of that, to pull the AUC value out explicitly. If you didn't, you get a whole bunch of information about the ROC and things.
All
like
very
that.
useful stuff.
Yeah.
No, not in our situation. If you're here, we're only interested in AUC. And here, once again, you can see our down-selected model. Well, it's not that bad, but
no, it's not as good as the other. It's not as good
as the other ones.
Yeah.
It's all relative.
So that's some simple model comparison, and I think next week we'll put a bow on this series by running this over the other models that we
and summarizing all this information, trying to give you as much knowledge and information as you can. It is like more than likely you're not going to be running one model when you're doing your machine learning or whatever. So knowing how to actually look at them and objectively compare across them, because they're also like, they can be trained differently, they can be giving you different pieces of information. Eventually you're going to need to go, at the end of the day, you're going to need to be able to go to your boss and go, hey, I trained a model, or I trained 50 models, I did these things based on my analysis, I looked at the different things, this is the model that we need to be picking. And it's also going to depend on a bunch of other stuff as well, like understandability of the model. Do you want it to be black box? Do you only care about predictions, or do you care about interpretability, like in English, and a bunch of other stuff? So there's other external stuff that you might want to consider, or you probably should be considering as well. But we wanted to give you as many tools as you possibly could have. Looking at that. And with that, I think we should call it here because we've gone through our entire script. So thank you all.
It's over.
It's done. So thank you all for joining us for episode 59 of TidyX, episode 7 I believe, of PitchFX. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick. And you can tweet us both at tidy_explained or Gmail us both at tidy.explained@gmail.com, or go to the GitHub page and open up an issue, or you can subscribe to the YouTube channel and leave some comments, feedback, things that you might want to see in upcoming series, etc.
etc. Thank you all so much, and keep on exploring your world.